All right, let us now use the slicing method to do some more generic problems. Example 2. Derive the formula V equals 4/3 pi r cubed, the volume of a sphere using the slicing method. So let's go back to the method, show you how to use it. Step 1, draw a picture including a cross section. Now, drawing a picture of a sphere is kind of hard for me. It kind of looks like a circle. And then, again, any cross section, if we cut a sphere horizontally, you can also do it vertically. We'll get into what that looks like later. If we cut this horizontally anywhere, well, we get a circle. Circle with some radius. Now the question is, at any height, and maybe let's say that the center of this sphere is 0, 0. So height here can be negative or positive. Or we could look at a hemisphere and just double it. At any height, what is the radius of this circle? Now this one's a little trickier. In the last one, we had a linear relationship. But here, at any height, it's not going to be a linear relationship, right? If you're looking at like these heights, the radius isn't changing very much, but it's much less steep over here. So the radius is changing a lot as the height goes up. So question is, how do we find this? What's the relationship between that height, h, and the radius of that cross-sectional circle? And this is 99% of the hard part for most of these problems. Okay, so like, again, we know that when the height is 0, the radius is just going to be that r. And when the height is r, the radius should be 0, but it's not linear. So to find this here, what we're going to do is we're going to look at this. Let's look at the side of this sphere, because we know the relationship between the y. Let's go into 2 dimensions real quick. Let's go into 2 dimensions. We go into 2 dimensions and let's just look at this semicircle. What's the equation of this semicircle right here? Well, a circle is x squared plus y squared is r squared. And that's exactly what we have right here. So at any point y, and let's rephrase this, at any height y, notice we can call this, let's not call this r right here. Oh dear. Come on, please erase. Thank you. Call it x instead. Because if we think of this as the origin and a sphere around the origin, the radius is just that x coordinate. The height is just that y coordinate. Right? This, if we think about this kind of in 2 dimensions, this is just the coordinates x comma y. Again, which in 2 dimensions looks like this. Coordinate x comma y. And really, we just care about that x. What's the relationship between this x and this y? If we can find that, we know the area of this cross section. If we know the area of the cross section, we know the volume of the sphere. So at any height y, what is x? Let's use what we know about the area of the equation of circles. Let's solve for y. We do that, we get y squared equals r squared minus x squared. For y is just the plus or minus square root of r squared minus x squared. Okay, so the plus or minus is a little annoying to deal with. We don't want to integrate pluses and minuses. So instead, let's just double. Let's not worry about these negatives. Let's not worry about anything down here. And let's just double it. Okay. So let's only look at the positive y values and positive x values. Oh, all x values actually, just positive y values. Let's look at hemisphere. We don't have to deal with that. So make sure, and I'm reminding myself too, make sure to double the area of a hemisphere to get our answer. So we know the area now of this cross section. It's a circle, so it's pi times whatever the radius is, which is x. And what is x at any height? Oh, I solved for the wrong thing. X is just it's going to be the same thing just with y's instead of x's, because x and y are essentially the same in this formula. So x squared is just going to be r squared minus y squared. We don't even need to solve for x. So the area is just going to be pi times r squared minus y squared. And again, you didn't have to do a horizontal cross section. You could do a vertical cross section as well. And then it's going to be in terms of x. So you can use either vertical or horizontal. Here the vertical may have made a little bit more sense, but this is good practice integrating in terms of y, which is absolutely fine. So the area, any cross section in terms of y is going to be this. That was step 2. Find the area of the cross section. Step 3 is to integrate to get the volume. And actually, yeah, we don't have to look at a hemisphere at all. You could look at a hemisphere and double it. Let's be consistent. I don't want to backtrack too much. So the volume is going to be double the volume of a hemisphere. So the upper half hemisphere is going to be when y starts at 0 and goes all the way up. All right, what's this max y value up here? Well, the max y value is just the radius of the sphere. And then what is the area? The area is pi times r squared minus y squared dy. And now we just integrate. So if we do that, let's take the pi out in front. We get the integral from 0 to r squared minus y squared. Again, this dy right here is really important. R is just a number. We're integrating all of this with respect to y. So taking the antiderivative with respect to y. So this is not r cubed over 3. That would be the antiderivative with respect to r. But here, think of this is just a number. What's the antiderivative of 4 with respect to y? It's just 4y. What's the antiderivative of 5 with respect to y? It's just 5y. The antiderivative of r squared, which is just some number, is going to be r squared times y. And then the other one is more normal. A value from y equals 0. And again, it's a good idea to remind yourself, if you have multiple letters, be very clear that, okay, these limits are for y. We get 2 pi, plug in r. We get r squared times r minus 1/3 r cubed. Again, we're plugging in r for y minus when we plug in 0 for y. And it's just going to give us a bunch of zeros. Well, what do we got? 2 pi times r cubed minus 1/3 r cubed. Well, that's 2/3 r cubed. What's 2 pi times 2/3 r cubed? 4/3 pi r cubed, just like we wanted. So these are the examples at the start of this section. And in my opinion, they're the hardest ones. This next example is what we're going to be doing for most of the section. I think they're not as bad, but we'll see. Let me know if you have questions. Example 3. Let's go back to pottery. Let's go back to this thing. We're going to look at this shape again. And in fact, let's really look at this shape. I don't know if it'll let me copy this. Because if I add a new page, then it's going to put it somewhere I don't want. But I can just manually drag it over here. Okay. So, example 3, we're going to do pottery again. The inner edge of this, I'm going to call it a vase. I don't know the right word. Pot. The inner edge of this vase can be modeled by the function x equals 2 minus cosine of y. So that's the graph of this blue side. If this is the y-axis, then this blue side right here is just x equals 2 minus cosine y. No period. Now the question is, oh, and this is in inches, and is about 3 inches tall. Will it hold a pint of liquid? Now, if you actually had this vase, you could answer this question very easily. You can measure a pint of water and pour it in the vase and see if it holds it. But let's say you don't have that. You're just planning on making this vase or something like that. I don't know. And you're curious if it's going to hold a pint. You can think of whatever liquid you want to put in this in this vase. If you want to make it more applicable to you, a pint of whatever you like to drink, orange juice, water, soda. I don't know. Probably should not put soda in pottery. I don't know. Anyway, probably shouldn't. I don't know anything about pottery. I'm going to be quiet. So we're just going to find the volume using slicing. So we already have this beautiful picture of a cross section and a beautiful picture of this vase. Well, what does this cross section look like? Again, it's going to be a circle. So any height, y, what's the area? Well, it's going to be, area is going to be pi times that x coordinate, right? That's the x coordinate. We can think of this as an x comma y. If we have an x and y axis like this, actually, sorry, we're in 3 dimensions, so the x and y axis will look like this through the center of the base of this vase. Hope y'all can draw better than I can. That's what they should have had in grad school for me, a drawing class. I should have taken one of those. All right, well, we have I said this is why it's easier. Because in the last problem, this was the hard part. Step 2, find the area of the cross section. That was really hard. We had to use all we know about geometry in both of these problems to get an area formula. But we're basically already done. All right, this is just pi times x squared. All right, this distance, this radius is always just x. We already have the relationship between x and y. Oh, so even though this looks way messier than a sphere looks super easy compared to this. But because it already gave us the relationship between x and y, we're basically already done. So example 1 and example 2, that's the hard stuff for this section. The nicer shapes are the harder ones, because otherwise, we are given some kind of function, it's easy peasy. Because look what happens. Well, at any height y, we know the x coordinate is 2 minus the cosine of y. So the area is just going to be pi times x squared, and x is 2 minus the cosine of y. Oh no! I made this example up squared. I made this example up to try to be like an interesting contextualized problem. But the integral is going to be harder than I wanted it to be. But we can do it. We can do it. The integral will be a little trickier though. It'll be a good review of U substitutions. Sorry. I can't even laugh or smile normally because of the surgery. Okay, it's fine. Good practice for this integration. So this is our area. And again, we could visualize this with Desmos if we wanted, if I can find my Desmos. Right, our x is just 2 minus the cosine of y. And specifically, we're saying that this is about 3 inches tall. So it's really this rotated around the y-axis. All right, this is the side. This is that blue side. Roughly. We're approximating. Here, we can even make it blue. Okay. So step 3 is now integrate. So the volume is going to be the integral. What is y going from? Well, we know it's about 3 inches tall. So we're going to start at the bottom at a height of 0. Right? We're starting down here at a y of 0. And we're going up here to a y of 3. Of the area, which is pi times the radius squared. And again, this is all in terms of y. Now, this is a fantastic opportunity for you to pause the video and see if you can solve this integral. It's a little tricky. I'm going to go through it kind of quickly because, again, this is chapter 1 stuff, and this is good to review, but I want to spend most of the time on chapter 2 stuff in these videos. So it looks like a U sub, but don't fall into that trap. If you let this be U, we don't have a du anywhere. We need a sign somewhere, and we don't have a sign. So we're going to have to FOIL it out. Let's take the pi in front. When we FOIL it out, we're going to get 4 minus 4 cosine of y plus cosine squared of y. And it's the cosine squared of y that really gives us an issue. We can integrate this, no problem. But we can't integrate this right now. So we're going to have to use a power reduction formula, a trig identity, in order to touch this thing. Hopefully, you've seen this somewhere before. That the cosine squared of any angle is just, what is it? 1 plus cosine of double that angle over 2, I think. I think that's a power reduction formula. I'm going to double check before I go on any further. I'm almost positive it's this, but I do want to make sure. Yep, that is indeed what it is. Good job. I'm congratulating myself. This is how far I've fallen. So what we have is we can rewrite this integrand. 4 minus 4 cosine of y plus cosine squared is just 1. Let's write it as 1/2 times 1 plus cosine. Actually, let's just save a bunch of steps and distribute the 1/2. 1/2 plus 1/2 cosine of 2y dy. And now we can do this guy with a u substitution. Whereas this guy, we cannot integrate. All right, and we could combine like terms and clean this up a little bit as well, right? We have a plus 1/2 and a plus 4. That's plus 4.5. But let's just get integrating. Remember, we're integrating with respect to y. So 4 plus 1/2 is 4.5 y. Antiderivative of cosine is sine. Get minus 4 sine of y. You could do a u substitution here, or you could divide by 2. Did really do a u substitution, but again, I don't want to take forever on this. And again, y is going from 0 to 3. Let's make sure, let's do a quick check that our antiderivative is correct by taking the derivative of this. The derivative of this with respect to y is 4.5. Good. We had that. 4.5. Derivative of this, negative 4 cosine. Great. Derivative of this, we have to have the chain rule, so it'll be a quarter times cosine of 2y times 2. Quarter times 2 is a half. So good. We have the right antiderivative. And now we can just plug in and see what we got. We're looking for the volume here. So it's going to be pi times, when we plug in 3, 4.5 times 3 is 13.5. Minus 4 sine of 3, whatever that is, plus 1/4 sine of 6, whatever that is, minus when you plug in 0. 0, sine of 0 is 0, sine of 0 is still 0. So we can't do this exactly. We're going to have to approximate it. Now for applications, approximation's okay. Usually, though, I want exact answers. But remember what our question is. Will it hold a pint of liquid? So we're finding the volume, but all we need to do is compare this volume to a pint. Well, let's use a calculator. What is this? What is this equal to? Approximately. Pi times 13.5 minus 4 sine 3 plus a quarter sine of 6. 40.419. Oh, that's way bigger than 1. But what are our units? Inches. So we found a volume with inches. That's going to be in inches cubed. How many inches cubed are in a pint? Heck if I know. It's the imperial system. There's no good. If we had like centimeters cubed and we were curious about liters, I'm pretty sure then there's a much nicer conversion. But there's not a nice conversion, so we're just going. You could do this in a long step by step. I don't care. We're gonna say 40.419 inches cubed to pints. Oh, that's about 1.4 pints. Thank you, Google. So will it hold a pint? Yes. Almost 1.5 pints. And that's our answer. A pint? Yes, it can hold a pint. Yeah, and if this were like a quiz question or something, I would give you the conversion. And you could do the conversion yourself, but there we go. We correctly found that this area, if we model the side with this function of our wonderful little pot vase thing, I don't know the word for this, can hold a pint with our approximation. I did estimate the size of this because it looks like the height is about the width of their hand. And then I just modeled it about by that trig function, which is a decent approximation, I think, from a picture, but I don't know. So there you go. That's this question. Let me know if you have any problems or if any questions. And yeah, until the next one. Bye-bye.